comes 1. This is 3 dimensions, 2 dimensions, but 1 dimensions also. Always this is 2. Okay. Now let me discuss more on primitive cell. In 3D, we have 3 non-coplanar primitive lattice vectors that I started with initially. Non-coplanar, that I have again made it red color to emphasize that they should be non-coplanar. So what is the volume of the primitive cell? A1 dot A2 plus A3. I have put a magnitude because A1 dot A2 plus A3 is triple scalar product, right? But sometimes it can become negative. Though it is a scalar, but it can become negative. So you must take the magnitude. So suppose you imagine that I dot j cross k, that is 1. But if you take minus I dot minus j dot minus k, that will become minus 1. That's why to take care of that negative sign, I have put a modulus again. You must take the magnitude. A1 dot A2 plus A3. Magnitude will give you volume of the primitive cell. In the 2-dimensional case, area is only given by A1 cross A2 simply. But here it's a scalar product, triple scalar product with the magnitude. So if the 3 vectors are coplanar, for example, you can span only 2-dimensional lattice. If you take coplanar vectors, you cannot span 3-dimensional lattice. You can only span 2 dimensions. That's why this should be non-coplanar lattice. So in general, if you see in 3 dimensions, general primitive cell is parallelepiped, what I have shown here. A1, A2, A3, different magnitudes and different angles they have between them. Where alpha is the angle between A1 and A2, beta is the angle between A2 and A3, and gamma between A1 and A3. These angles are different and lengths are different. Then you get a parallelepiped. That's the most general primitive cell actually. Okay. So you see that if you have the 3-dimensional primitive cell, what it has an A1, A2 plane, right? A1, A2 constitute a plane. And if you keep on extending A1, A2 plane, you get a 2-dimensional lattice again. And it also has A2, A3 plane, A2, A3, A2, A3 plane. That's like a YZ plane actually. If you extend that plane, you will get another 2-dimensional lattice. And it also has A3, A1 plane, A3, A1 plane. That's like ZX plane. So A3, A1 plane, if you extend, you will get another 2-dimensional lattice. So any particular plane in 3-dimensional lattice, if you extend it, you will get 2-dimensional lattice. It is just a combination of 2-dimensional lattices. Okay. So, and in general, A1 is not equal to A3, not equal to A2, not equal to A3. These I have not put this bold face. Bold, once I remove bold face, they become the magnitude. If I put bold face, means they are vectors. And alpha not equal to beta not equal to gamma. In that case, only you get parallelepiped. This is the most general case. Okay. And if you get point P, suppose I want to express point P as a combination of A1, A2, A3, just see that RP is equal to A1 plus A2 plus A3 simply. A1, A2, and A3. A1 plus A2 plus A3. That means N1 is 1, N2 is 1, N3 is 1. So like this, you can express for all points. For any point you take, you can express it as a linear combination of A1, A2, A3. Okay. Now, as I told you, all periodic structures are not Bravais lattices. One best example what we have is 2-dimensional honeycomb structure. 2-dimensional honeycomb is nothing but take hexagons, regular hexagons, and pack them like this, the way I have shown here. Okay. So this is not a Bravais lattice. So from the definition, we can understand and say that why it's not a Bravais lattice. So you see, suppose when you have this kind of structure, it is periodic. There is no doubt. It is periodically arranged. Okay. So now I take 3 points P, Q, and R. So let us look at the symmetry, because I told you definition of Bravais lattice is all points should have the same symmetry and orientation also. Suppose if you take point P I have shown here separately. You see around point P, it is looking like this actually, symmetry. Okay, so it is like line is towards the right and this other 2 atoms are on the left side actually. But if you take point Q, it just inverted. You see point Q, this becomes inverted, line comes this way actually. Okay, so what is the relationship between these two? They are not same. Point P has a different orientation. Point Q has a different orientation. So, but they are not satisfying your Bravais lattice definition actually. And point R, if you see again, point R, you see, you get back the same again. P and R have the same. Point P and point R have the same symmetry, same orientation they have. But point Q is inverted orientation. If you rotate the orientation at point P by 180 degrees, then you get point Q actually. That means P and Q are not having the same symmetry. Because of this reason, This two-dimensional honeycomb is called honeycomb structure somehow. Two-dimensional honeycomb is not a Bravais Lattice set. Okay, so it's not only P, you can take any PQR, it doesn't matter. You take any points, always you find that adjacent points are not in the same orientation. Any two adjacent points you take, they are always different orientation. That's how the structure is. That's why two-dimensional honeycomb is not a Bravais Lattice, but we can make this into Bravais Lattice. I will tell you later. We'll discuss more about it. We can make this into Bravais Lattice by redefining our basis. We'll come to that later. But at present, with a single point basis, two-dimensional honeycomb is not a Bravais Lattice. Okay, so we have 5 Bravais lattices possible in 2 dimensions. Only 5. Okay, so first one is square lattice, simplest one. A is equal to B and gamma is equal to 90 degree. And second one is rectangular lattice. A not equal to B but gamma 90 degree. Third one is centered rectangle. In this rectangular lattice, you took one center of the rectangle on one dot X. Center rectangular lattice. A not equal to B, gamma 90 degree. Then you have hexagonal lattice. This hexagonal lattice is not same as your honeycomb structure. That is the honeycomb structure. What happens in the hexagon? In between the hexagon, there is no point. The hexagonal lattice has a point in between. If you complete this hexagon completely like this, you see that at the middle you have a pointing. But in honeycomb doesn't have central pointing. It's only hollow hexagon. Okay, that's the difference. That's not a Bravais lattice. Hexagonal lattice is different. So this is the Bravais lattice, and A is equal to B, and gamma is 120 degree. And that's this is not rectangular. This is a mistake I've written. This should be it's oblique lattice. Fifth one is actually oblique lattice. It's not rectangular. Rectangular is already on. So probably I cut pasted it, so it remained. The fifth one is actually called oblique lattice. Means A and B they are not equal. Gamma is not 90 degree. That's called oblique lattice. These are the only 5 possibilities you get in 2 dimensions. But we will not discuss much about these 2-dimensional lattices because you see, when you study solid-state physics, first we are going to do 3-dimensional Bravais lattices, not 2-dimensional. 2-dimensional are required only when you do surface physics. When you talk about surfaces and surface reconstruction, etc., then you will talk about 2-dimensional lattices. Otherwise, these are not much important for the bulk properties of solid-state. Okay. So, just I want to tell you what are the possible. But somebody might ask, why not centered square lattice? As you have centered rectangle, why not centered square? Suppose you put a point at the center of all the squares here, the first case, you will see that again that will become a square lattice. Because when you put it at the center, it will become a square lattice. Maybe its square dimension will be different, but it will remain again square lattice. Okay, that's why you don't have centered square lattice. Centered square lattice is same as square lattice. The dimensions are different, but it still looks like a square. Because if you connect the diagonals of the square, you will get actual 4 squares again. You know that. That's why putting a point at the center of the square lattice will not give you any new lattice actually. Whereas rectangular case, you get a new lattice. Okay. So these are the only possibilities. Please correct the last one, 5th one. By mistake, I have written rectangular lattice. That is wrong. It should be oblique lattice. Okay. So now let us see. So far we are talking about lattice, but how it is related to crystal? How the lattice is related to crystal? If you take a crystal structure, that is actually called lattice with a basis. That means you must have a base lattice, and you should know what is the basis. Then you can get a crystallite. Okay. So each point in the Bravais lattice corresponds to a basis. Okay. Each point in the Bravais lattice corresponds to a basis. Because I told you that Bravais lattice is nothing but a set of lattice points only, mathematical construction. Okay, so you just put points at the periodically arranged points. Now each point has some meaning actually. In reality, for the crystals, each point corresponds to a basis. What is that basis means? Basis is nothing but it may be a single atom or a group of atoms or ions also sometimes. It can be ions also. So generally, it's a basis is nothing but a group of atoms. So that means if you replace each point in the Bravais lattice by a group of atoms, you get a crystallite. Okay. Because now crystal is real, but lattice is not real. Lattice is a mathematical construction only. It has no reality. But you can make it real by adding basis to it. That means lattice plus basis is equal to crystal. That's what I can say. Crystal and lattice are related this way. So if you know what is the lattice, if you know what is the basis, you can make a crystal lattice. Now let us see a simple example and show you here in two-dimensional. Suppose I have taken this square lattice. I've started taking square lattice simply, and just I add a basis like this. My basis is nothing but triangular. We have a triangle. Each corner is occupied by an atom. Okay, this is my basis. Basis can be anything. You can have a three-dimensional basis. You can have a basis which is like a dipole, two charges at, separated by a short distance. Anything you can have. But I have taken a basis like this. Now, if you want to get the crystal, what I should do? You just remove these lattice points. At each point, you put this basis here. So this is my crystal. This is real. Crystal is, you can see the crystal, but you can't see the lattice. Okay. So once you do this, you get a crystal like this. So basis, don't think that basis should be some regular equilateral triangle or something. No, not necessarily. You can have any regular shape. You can have any shape for that. It doesn't matter. Because any molecule you can have there, any group of atoms arranged in any certain way, it doesn't matter. Only thing is, you have to, when you place it on the lattice points, you must place it exactly in the same orientation. You should not rotate it. You see, all the triangles I have put here, they are in the same orientation. If you rotate, that fails to be a crystalline. It should have the same orientation. So this is lattice plus basis will give you the crystal. So what is this basis in 3 dimensions? We will discuss much more about these things later. Okay. So this basis for the crystals, you can have suppose sometimes maybe a cube can become a basis for you, where atoms are there at the corners and the body center. That can be a basis for it. It all depends what kind of structures you are studying. So the main important point in this slide, what you have to understand is lattice. When you add basis to it, you get the crystal. So what is the basis? That you have to know. If you know what is the basis, what is the lattice, you know the crystal. But for all the theoretical studies, what we do is we assume the lattice. We take the lattice and do the things. For example, if you are talking about X-ray diffraction. X-ray diffraction depends on the lattice, how the planes are oriented. But X-ray intensity, if you want to calculate Bragg law, you don't need basis. Just lattice suction, lattice planes, and you can derive Bragg law. So Bragg law simply tells you at what angle the reflection is coming, but it does not say what is the intensity of reflection. To calculate the intensity of reflection, you must know what is the basis. Basis tells you what is the intensity. Okay, that will give the real crystal diffraction. Okay, so this is the difference between lattice and crystal. Okay. So yeah, this point I have told you already. Basis should have the same orientation at all points. Okay, so now I want to give you one more example of the crystal actually. This is again I have taken square lattice, but this time my basis is different. I have, let's say, diatomic molecule. One atom is bigger, other one is smaller. So just replace all the points with this diatomic molecule. Exactly the same orientation. Don't change the orientation at any point. Okay. So in the previous case and this case, in both the cases, lattice is a square lattice I have taken, but basis is different. Okay. So when you study such a structure using X-ray diffraction, both that will say that it's a square lattice, but intensities will be different. Because intensities depend on the basis, not on the lattice. So crystal is also infinitely extending like lattice, because it will place at each point of the lattice, you have to place this basis. That means it is infinitely extending again. But is it possible to make infinitely extending crystal? That's not possible. You cannot make an infinitely extending crystal. We cannot exist actually. It will be covered in the crystal, right? So that is not possible to have infinitely extending crystal. So, but real crystals are of finite size. Maximum crystal size maybe you can get 1 centimeter. Then that is very difficult. 1 centimeter crystal is very, very difficult. Only for silicon you can get because that is different. But generally crystals cannot be obtained in large size. So how the concept of lattice is applicable to real crystals? Then the real crystal is truncated. It has only finite size. How can you apply concept of lattice to that? You can apply because how we apply is like this. If you take any finite crystal, macroscopic size crystal, not nanometer size, that is different. Nano comes in a different way. But if you take any macroscopic size, 1 mm, 1 centimeter. So what will happen is number of atoms residing on the surface of any macroscopic crystal is negligible compared to the atoms residing in the bulkhead. Surface atoms can be neglected. Number of atoms can calculate. We take 1 centimeter cube and assume that 2 angstrom Lattice parameter and arrange them and see how many are there on the surface, how many are there inside. So surface number of atoms is extremely small actually compared to bulk atoms. So you can neglect the surface atoms. If you do that, you can apply lattice concept to finite crystals also. But if you go into very, very small crystals like nanometer sized crystals, then the problem arises. In that case, what happens? Surface atoms and bulk atoms may be of the same number, or sometimes surface atoms may be more. In that case, you cannot apply this concept. That's why when you go to nano level, then you cannot apply the concept of lattice there. But otherwise, for real crystals, macroscopic crystals, it is very well validated. Surface effects are negligible basically. Okay. Now let us. Most of the time we talk about unit cell. We never talk about primitive cell like that. Primitive cell is a concept to explain Bravais lattice, but unit cell is mostly used. Why the unit cell is used? So because now, if you want to draw the lattice, as we know that it's infinitely extending, is it possible to draw whole lattice? Nobody can draw it. That's not possible. But if you can find a small block which will have all the symmetry of the lattice, then that unit will be very useful to you. For example, that is called a unit cell actually. So a small portion of the lattice is taken which possesses full symmetry of the lattice, and that is called a unit cell actually. That means unit cell, primitive cell and unit cell have major differences like this. Unit cell has the symmetry of the lattice. Suppose if you are talking about cubic solid, your unit cell is cubic, but your primitive cell is not cubic there also. Primitive cell is different. It can have any shape actually. I told you, primitive cell is not unique. But the unit cell for a cubic solid is cube actually. So this is actually a definition you can use it like this. A unit cell is a region that just fills the space without any overlapping when translated through some subset of Bravais lattice vector. That means we take a unit cell and try to translate it. We have Bravais lattice vectors actually. We can just translate it with Bravais lattice vectors. If we do use all the Bravais lattice vectors, we may have a lot of overlaps actually, because unit cell is slightly bigger. So you may do rescanning, spanning again and again some points. If you don't want to do that, you have to only choose some subset of Bravais lattice vectors and translate it to span the lattice. That is called unit cell. But this will not give you much feeling actually. That's only because textbook definition I have given you. But actually, unit cell you have to remember like this. Unit cell possesses full symmetry of the lattice, whereas the primitive cell in general does not possess the symmetry. There are very rare cases, special cases where primitive cell and unit cell are same. Actually. For example, simple qubit. There is a primitive cell also and unit cell also. Okay. So just 1 minute. Okay, so the primitive cell does not possess the symmetry. But you might ask, what is the use of that? No, primitive cell is useful in the sense because primitive lattice vectors are very important for you. Primitive lattice vectors are the most important thing. That's why we are getting the primitive cell. But generally, when you want to look at a crystal, if you have a unit cell, by just by looking at the unit cell, you can say what kind of symmetry the crystal has or lattice has. But just by looking at the primitive cell, you can't say that. That's why the concept of unit cell is used regularly in our solid state physics. Okay. So now, what is the relation between unit cell and primitive cell? Because volume of the unit cell is equal to integral multiple of the volume of the primitive cells. Because what happens in the unit cell will contain more than one lattice point. If you want, I can tell you about a body-centered qubit, for example. You take that unit cell has 2 lattice points, right? It will contain always integral number of lattice points. Okay, so but unit cell contains integral number of lattice points. Volume of the unit cell is integral multiple of the volume of the primitive cell, because you know that one lattice point is one unit primitive cell. If you have 2 lattice points, that means 2 primitive cells. That means unit cell is equal to 2 primitive cells if it is 2 lattice points. So that means you can relate unit cell volume to primitive cell volume by number n. N is equal to 1, 2, 3. If n becomes 1, they are equal. That is only special case, simple qubit. If n is equal to 2, that is body-centered qubit, because unit cell volume is twice the volume of the primitive cell. We will discuss. I will give you also some questions on these things because volume of the unit cell must be integral multiple of the primitive cell volume. It's simple. Because body-centered cubic if you take, it has the volume of A cube, for example. Okay. But primitive cell volume will be A cube by 2 actually. Without calculating, you can say, because we have two lattice points in A cube. What is the volume of one lattice point? A cube by 2. That's what the way it works like. Okay. So V unit cell for n is equal to 2, that you will get 2V actually. Where small v, the primitive cell volume. So they are always related, like you must remember this thing. Unit cell volume is integral multiple of primitive cell volume. So what is n depends on what is the structure we are discussing. So unit cells are useful in that way because by looking at the unit cell, you know what is the symmetry of the lattice. But primitive cell does not say the symmetry of the lattice. But there is a special primitive cell that is called Wigner seed cell, which is very, very symmetric. It tells you all the symmetry of the lattice. But Wigner seed cell, the shape of the Wigner seed cell is so complicated that cannot be used for any theoretical studies. That's why the Wigner seed cell is defined, but that is not used actually mostly. That is a primitive cell. It contains only one lattice point, but it has all the symmetry of the lattice. Very interesting. But its shape becomes so odd shape, it's difficult to use. But same Wigner seed cell in reciprocal lattice, that's called the Breloun zone. That is most used there actually. But we don't use much of Wigner seed cell in real lattice. We'll discuss those things later. Okay. And if you are talking about crystal systems and Bravais lattices in 3 dimensions, we have 7 crystal systems and 14 Bravais lattices in 3 dimensions. Why only 14? The question is, this can also be answered. People have theoretically worked out all the crystallographers and they have only found 14 Bravais lattices are possible. But if I want to discuss all those things, for that I have to tell you what is group theory, point groups, all these things have to be enumerated, which is very, very cumbersome and involved thing yet, which is not required now. Let's say that only 14 Bravais lattices are possible. They are divided into 7 crystal systems. Okay. So, and also I forgot to tell you one point because all these diagrams I took a lot of time to make these things actually. Because I cannot copy somebody's diagrams because then for a talk also you should not use downloaded content actually, never. But if that person knows about it, he can complain actually. So one should not use net downloaded content for anything actually. Everything you should make by yourself. I made all these things, so many complicated things. I took a lot of time actually. Okay, that doesn't matter, but somehow I made it. So first one is most symmetric one is cubic system. A is equal to B is equal to C, alpha is equal to beta is equal to gamma. What is alpha, beta, gamma? Somewhere I have defined it. Alpha means angle between A and B. Beta is angle between B and C. Gamma is angle between C and A. These are the angles defined. In cubic system, you have 3 Bravais lattices. In cubic system, you have 3 Bravais lattices. One is simple cubic, body-centered cubic, and face-centered. So simple cubic looks, all of you know these things, it is nothing new I'm talking. So simple cubic is, in simple cubic, effective number of lattice points is only 1 lattice point because each corner contributes 1/8 of a lattice point. So total number of lattice points, effective number of lattice points in the cube is 1. So this is a primitive cell. I told you before also, because simple cubic cell is a unit cell and also it's a primitive cell. It shows what is the symmetry. It says that it's a solid is cubic solid. And also it has only 1 lattice point. It's a primitive cell also. Okay, it's a special case. Then when you come to BCC, you have one extra lattice point. And one more thing, never use the word atoms for this. As long as you are talking about lattices, you always say lattice point only. That lattice point may correspond to a group of atoms in reality. So we will not talk about that. We always talk lattice point. So you have 1 lattice point at the body center of the BCC, and the effective number of lattice points is 2 lattice points. So that's why this is a unit cell, it's not a primitive cell. Okay. And if you see FCC, you have 4 lattice points because you have 6 faces contributing, 6 into 1 by 2, that is 3, and 8 corners are contributing 1. Total 4 lattice points. This is also unit cell, it's not a primitive cell. And the first one is primitive cell. For each crystal system, you get 1 primitive and other non-primitive cells. So that means in case of cubic system, you have 3 Bravais lattices. And other thing here is I told you that there are 2 lattice points in BCC. That means what is the volume of this BCC, that cube unit cell volume A cube. So A cube volume contains 2 lattice points. What is the volume of one lattice point? A cube by 2. That is the primitive cell volume actually. I also told you primitive cell volume, anyway you construct your primitive cell, volume remains same actually. For body centered cubic lattice, your primitive cell must have a volume of A cube by 2. How you construct your primitive cell is immaterial actually. Okay. Similarly, in this case, primitive cell volume is A cube by 4 actually for FCC. So you don't have to calculate, just taking always again A1, A2, A3, A1 dot A2 cross A3, you don't have to do that. Just by knowing the volume of the unit cell, you can find out what is the volume of the primitive cell. Sometimes we ask these questions actually in a PhD interview and all. People are usually confused. They are not able to relate. They are always related. I told you also, volume of the unit cell is integral multiple of volume of the primitive cell. Suppose let's say volume of the primitive cell is small b. In this case, it will become 2 into v. Here it will become 4 into v. Just 4 lattice points, 4 into v, 4 into volume of the primitive cell. Yes. Okay. So now next system comes out to tetragonal. Tetragonal is A is equal to B, not equal to C, but alpha is equal to beta is equal to gamma is equal to 90. In this, we have only two possibilities. One is simple tetragonal, and the other one is body-centered tetragonal. So simple tetragonal means we have only atoms at the corner. It's a primitive cell actually. If you take effective number of lattice points is 1 actually. But in the body-centered tetragonal, we have effective number of lattice points is 2 actually. But why not face-centered? People might ask actually. So people have already worked out, if you take the face-centered tetragonal lattice, that can always be converted into either simple tetragonal or body-centered. So you don't have a separate lattice actually. So, but I cannot show all those things, how to convert it and all those things, but we believe that there are only two possibilities in tetragonal system. But it's worked out, people have worked out and found only two are there. If you try to put at the faces one atom and see, that can be converted either of these two, one of them. You can make it. You don't have a separate face center lattice. Okay. So the third one is orthorhombic system. Ortho indicates that angles are 90 degree. Alpha is equal to beta is equal to gamma is equal to 90 degree. But A not equal to B not equal to C. Okay. So in this case, you can again have a simple orthorhombic where there are no atoms in between, only corners are occupied. Because in this case, you have only one lattice point. There is another possibility here. This is called base-centered orthorhombic. Base means this lower part. Once you have a lattice point in the base, you should also have a lattice point at the top also. Otherwise, it does not follow the translational symmetry. So when you translate this point above by C, you should go to the point. So base-centered actually means at the base and the top also. Both lattice points have to be there. Okay. In this case, 8 corners will contribute 1, and this base contributes half, top contributes half. That is 1. So 2 atoms, 2 lattice points are there. Base-centered orthorhombic. And we can also have body-centered orthorhombic. These also true. Here also we have 2 lattice points. Okay. Because corners will give you 1 and body is 1. So 1 plus 1, 2. These also true. And base-centered orthorhombic. And anyhow, there are crystals, real crystals are bound with this kind of structures, tetragonal, body-centered tetragonal. Structures are there actually. We will discuss those real crystals later. We are only going what are the possible Bravais lattices and crystals. You can also have face-centered orthorhombic, like your face-centered cubic kind of thing. You can also have face-centered orthorhombic. These are the 4 Bravais lattices are possible in orthorhombic system. Okay. Cubic have 3, tetragonal have 2. Orthorhombic has 4. This is the maximum number of Bravais lattices possible only for orthorhombic system. And then I can have monoclinic system, A not equal to B not equal to C, alpha not equal to 90, beta is equal to gamma is equal to 90. And sometimes, see, don't worry if somebody writes beta is equal to 90, alpha is equal to gamma is equal to, suppose beta not equal to 90, alpha is equal to gamma is equal to, that doesn't matter. It all depends on how they define angles. I have already told you, our angles are defined in such a way that angle between A and B is alpha, B and C is beta, C and A is gamma. That's the way we define according to this definition. So in this case, you can have 2 Bravais lattices, one simple and base-centered, simple monoclinic and base-centered. So there are 2 Bravais lattices in this kind of crystal system. Then you have hexagonal system. A is equal to B, not equal to C. And alpha is equal to 120 degree, beta is equal to gamma is equal to 90 degree. So this is called hexagonal system. So hexagonal is only simple hexagonal is possible. Breve lattice, only simple hexagonal Breve lattice. But people might think that hexagonal closed faculty is there. People must have heard hexagonal SCP lattice, but that's not a Breve lattice. That's why that doesn't come here. Right? Hexagonal SCP structure is non-Breve lattice. But why that is studied? Because there are many elements crystallized in SCP structure. That's the reason they study that. But we'll discuss thoroughly about SCP lattice later. Okay, but that's non-Breve lattice. Then sixth is rhombohedral system. Rhombohedral means A is equal to B is equal to C, alpha is equal to beta is equal to gamma. All angles are equal, but they are not equal to 90. This is only one Breve lattice possible, rhombohedral. There are a lot of compounds have this rhombohedral structure. So actual crystals and compounds we'll discuss maybe later. Okay. Yeah. Then 7 is, I told you 7 crystals, triclinic system, which is more odd-shaped crystal length. That's A not equal to B not equal to C, alpha not equal to beta, gamma not equal to gamma, and they are also not equal to 90 degrees. This is only one Breve lattice. So how many total number of Breve lattices we have? 3 for cubic, 2 for tetragonal, 4 for orthorhombic, 2 for monoclinic, 1 hexagonal, 1 triclinic. Total 14 Breve lattices and 7 crystal systems. But if you want to really enumerate 14 Breve lattices, why only 14 Breve lattices? That all can be done. For that, you need to have the group theory, this rotation operations. What are the what fold, like it's, you know that 5-fold symmetry does not exist. What are the symmetry axis, rotation axis? All those things one can consider and discuss about point groups. From that, one can enumerate 14 Breve lattices. It is possible, but at the beginning, better not to go into that. These are, you assume that these are given, can take it for granted. Okay. But that can also be derived. We did it during our PhD time, but in MSc or BSc level, that's not expected. Okay. So now, in reality, suppose so far I am talking about primitive lattice vector A1, A2, A3. Okay. Suppose when I am talking about A1, A2, A3, as long as orthogonal systems are concerned, orthogonal means what? Suppose cubic, tetragonal. These are orthogonal systems. Axis can be 90 degrees. But there are other crystal systems. For example, hexagonal. All the axes are not 90 degrees. When you have oblique axis, your mathematics is very, very complicated. If you just think of take x and y axis, not at 90 degrees, but at an angle alpha. Try to find out what is the equation of straight line in that. It will become very, very complicated. That's why crystallography is very complicated, because all crystals are not having alpha, beta, gamma 90 degrees. They have oblique angles also. For example, hexagonal case, we have 120 degree angle on the plane axis. Other angles are 90, but 120 degree angle. So that makes the crystallography very complicated mathematically. Even calculation of XID also becomes very complicated. That's why in most of the cases in textbooks, what they do, they take only cubic systems or tetragonal systems to discuss these things. And they go with that, because in this case, you can align your XYZ axis along A1 into A3. That is possible because they are orthogonal. A1 and A3 are orthogonal. Otherwise, if A1 and A3 are not orthogonal, how can you fix your x-axis along A1, y-axis along A2? That's not possible. You have to have oblique axis mathematics, which is very complicated. If you have done, they can do also. You also think about it. You take simple x and y axis with an angle alpha between them, but try to find out the equation of a straight line. It's very, very complicated. So that's why most of the things are discussed with respect to lattices which have orthogonal axis. For simple cubic, if you take simple cubic case, what is A1? A1 I have fixed along A1. I have fixed x-axis. I have fixed y-axis along A2, along A3 z-axis. Then I can write A1 as A into I cap, because I know that all the sides are equal. A into I cap. A2 can be A into J cap. A3 can be A into K cap. So it's not only talking A1, A2, A3, but we can also define according to our unit vectors ijk also we can write. Okay, now how many number of lattice points are there in this unit cell? We have only one lattice point. So it's a primitive cell with volume A cube, because each side is a volume A cube. It possesses cubic symmetry. So it is a unit cell, because the symmetry is there, because it is a symmetric primitive cell, it can be called as unit cell also. So in this case, primitive cell is same as unit cell. So number of nearest neighbors. How to find number of nearest neighbors? Because if you take any corner point, we imagine that it is sharing one atom here at a distance A. Another, sorry, I should not call it atom, one lattice point at distance A, another lattice point here. If you extend it down, there will be down one lattice point. There is one lattice point here. and there is one lattice point on the other side. So you will get only total 6 actually, nearest neighbors to any particular corner. Because if you take this corner atom, you have 3 already there. Another 3 will come if you extend the cube set on the sides. So you will only get total 6. Because in a single cube, you will not be able to realize this. You have to extend the cubes on top and the sides, then you can realize that only 6 nearest neighbors are possible for simple cube. What is the nearest neighbor distance? That's A only. What is the distance between these two? That is A. Because that's parameter. Only it looks like I've written spelling wrong. Polonium. Only one element. Polonium crystallizes in simple cubic structure. Over periodic table, there is no simple cubic structure except polonium. Okay. So this is the way you can, in reality, about XYZ axis, you can define A1, A2, A3 primitive vectors. This is important. Why I am writing this? When you go for reciprocal lattice, all these vectors are important to convert to find the reciprocal lattices for corresponding to this Bravais lattices. Okay. Now, if you take Bcc structures, look, I can do one. I have again aligned X, Y, and Z like this. I can take A1 is equal to A cap, as I showed you. A2 is equal to AJ cap. If I take A3 is equal to AK cap, then what will happen? You have an atom at the middle atom. When you try to write in terms of A1 into A3, you will not get integral coefficients. You will get half into A1 plus half into A2 plus half into A3 like that. So middle, if you take A3 along Z axis, that will not work for this, because according to your Bravais lattice definition, if you have A1, A2, A3 primitive lattice vectors, all the points in the Bravais lattice must be expressed or can be expressed as N1, A1 plus N2, A2 plus N3, A3, where N1, N2, N3 are integers. But if I take my A3 along Z axis, then because you have an atom at the center, that cannot be expressed as integral multiple of A1, A2, A3. That's why you should not choose XY is okay. 2 you can. The third one, you should take the body centered atom, A3. That is A by 2 into I plus J plus K. You must take it that way. Otherwise, you will not be able to go into this atom at all, this lattice point at all. Because if you have AI, AJ, AK, either you will come here or you will come here. In between, you will not go. If you want to go, you have to use fractional multiples. That is not allowed. So you must define A1, A2, A3 like this. But sometimes what happens, you are able to define primitive lattice vector more symmetrically. That is very useful when you construct reciprocal lattices. And also in any case, not only for reciprocal lattices, if you have the symmetric vectors, they are always useful mathematically. Your work becomes easier. So how can you define symmetric primitive lattice vectors here? Suppose you see at the origin, I have 3 planes intersecting. One is XY plane, XZ plane, and YZ plane, right? So for each plane, I take the body centered atom directly below this. I take a body centered atom on the left side of this. I take a body centered atom on the back side. That means for A1, suppose I have defined A1 is no, this doesn't work. This A1 is different, because symmetrically, if you want to define, your A1 will become atom which is behind this YZ plane. That we have to take. That will become A by 2 to J plus K minus I. And A2 becomes A by 2 to K plus I minus J. I could have drawn the big diagram I have to draw, because if I want to show these vectors correctly, I need to show at least 1, 2, 3. 3 more cubes I have to draw here. It becomes very complicated, and board we used to do sometimes. But anyhow, that doesn't matter. But what I am taking here is, you take a unit cell below the XY plane. You take the body center of that. That is one, A1. Similarly, A2 on the left side. A3 on the back side of YZ plane. If you take like that, you will get A1 is equal to A by 2 into J plus K minus I. Because if you take YZ plane, if you extend your x-axis behind, you will get that will become minus I capital. J plus K means YZ plane. If you go back, that is J plus K minus I. That is A1. A2 will be A by 2 K plus I minus J. K plus I means XZ plane. On the left side, you have to think of. You have to think of a point here. That is K plus I minus J. A3 is equal to A by 2 into I plus J. That is below the XY plane. I plus J minus K. You can define the primitive lattice vectors more symmetrically like this. What symmetry it has? JKI, KIJ, IJK. A1 means I cap is negative. A2 means J cap is negative. A3 is K cap is negative. So this most symmetric vectors you can define. So what is the symmetry here? If you look at this, you take the body diagonal of this cube. Okay, just extend this A3 to the point here. You get the body diagonal. So these vectors make equal angles with the body diagonal. If you want, you can find those angles. Body diagonal is nothing but A by 2 into A into I plus I cap plus J cap plus K cap. So with this vector, they make equal angles. You can also find the what is the angle also. But that way they are symmetric. These vectors are symmetric compared to because here you see in A3 you have IJK, but in A2 you have only J, A1 you have only I. But here they are not like that. A1, A2 all have IJK. Okay. Anyway, this already I have told this thing probably. Yeah. So number of lattice points we know it is 2. Unit cell volume is A cube. Primitive cell volume is A cube by 2. I have told you already. 2 lattice points A cube. 1 lattice point is A cube by 2. Number of nearest neighbors. Here it is very easy. You just stick to the central point, central lattice point, because you have 8 corners and we have 8 atoms, 8 lattice points symmetrically distributed around the body center. That is the nearest number of nearest neighbors is 8. And nearest neighbor distance is A root 3 by 2 because if you take the body diagonal, that is A root 3. Half of that is the distance. The distance. All are at the equal distance from the center, that is A root 3 by 2. That is the nearest neighbor distance. Okay. So Bcc structure is also not very common. For example, iron crystallization Bcc structure. FCC is very common. So these are symmetric vectors are very important. If you don't understand this, tomorrow sometime I'll try to draw the big square and I can show you actually. Okay, okay. Then FCC. FCC structure as I have already showed you, but in this case, you can make see this the original FCC structure is in the right side actually. As all the face centers are occupied. But I have removed some of the face centers here to show you that easily what is A1, A2, A3. Suppose A1 is YZ plane, right? Center of the plane behind. That is A1 is equal to A by 2 into J plus K. A2 is equal to A by 2 into K plus I because K for Z and I for X. And A3 is equal to this one, XY plane. That is A by 2 into I plus J. So you see that these are already we have done it symmetrically. If you want to write non-symmetric vectors, you can also write like this. A1 you take AI cap, A2 you take AJ cap, and only one face center you can take, A3. That you can define, but that is not important. Symmetric lattice vector will directly define what we do. We have taken face center of the lattice points of the planes which are intersecting at the origin. So you see there are 3 planes intersecting at the origin. This is my origin. And one plane is YZ plane, other plane XY plane, and XZ plane. All these 3 planes now face centers. Those atoms if you connect, you will get a symmetric primitive lattice vector. Okay, so that's why A1 means you don't have I. That's the symmetry it has. A1 doesn't have I. A2 doesn't have J. A3 does not have K. J plus K, K plus I, I plus J. That's the most symmetric primitive lattice vectors. So what are the number of lattice points? We have 4. It's a unit cell with volume A cube. What is the primitive cell volume? A cube by 4. Because we have 4 lattice points is corresponding to A cube volume. One lattice point is A cube by 4. So just by knowing the volume of the unit cell, we can know what is the volume of the primitive cell. But what is the shape of the primitive cell? It depends on how you choose your A1, A2, A3. This is one way I have chosen. Okay. This is one way. You can, if you just extend this into this thing, you may get some shape, but it's not easy to imagine that shapes. Don't worry about it. You just complete this parallelepiped with A1, A2, A3, you will get some shape. But if you redefine your A1, A2, A3, you will get a different shape. But all the shapes, primitive cells, will have the same volume, A cube by 4x. But what we have given here is most symmetric primitive lattice vectors. Yeah. Now, in case of FCC, realizing, did I say for FCC? Yeah. Yeah. In case of FCC, realizing the number of nearest neighbors, not that easy. Like BCC. BCC because you have a body-centered lattice point and 8 corners are connected. It's very easy. 8 lattice points. Okay. So that means number of nearest neighbors are 8, and near neighbor distance is A root 3 by 2. That's very easy. But a face center is not that easy. That's why I have drawn 2 cubes nearby here. Okay. And let us concentrate on the red lattice point, which I have shown in the middle plane. There are three planes I have drawn, you see. This violet dots I have put. All the violet dots, lattice points, are the nearest neighbors to this red dot actually. And they all have the same distance from the red dot actually. Let us see what is the distance. Suppose if you take this central plane, okay, you have a red dot at the center of the square, and distance to the corner will be a by root 2, right? Because diagonal of the square is a root 2 and a root 2 by 2. So distance to any of the corners is a by root 2. But not only that, to the corner, you take another point which is on the left side plane. I have connected it by dotted line actually, you can see. You go a by 2 above, a by 2 to the left. Then you will get a lattice point here. That distance is also a by root 2. And calculate it and see actually what. So all the points which are indicated by violet color are at equidistant from the red dot at the center. So how many dots are there? In the first plane, each plane you see 4 points are there. The left side plane you have 4 points. Right side you have 4. The centered one you have 4. 3 into 4, 12 lattice points. There are 12 lattice points which are nearest neighbors to the face centered plane. So this is very important. Geometrically you have to see. And each that near neighbor distance is a by root 2. That's very important. All have the same distance. Maybe because you think that they're in different plane, it doesn't matter. 3 dimensions, just connect them. If you want to travel from the center to any of the lattice points, you can go a by 2 in one direction. A by 2, it's perpendicular direction. You will get it. Except for the lattice points in the plane. So this is a very important thing, and if you have any confusion, you can ask me later. But you just look at the diagram properly and realize that all that 12 atoms, lattice points, whatever I indicated by violet color, they are at equal distance from the central lattice point. That's why it has 12. Near neighbor, number of nearest neighbors are 12, and near neighbor distance is a by root 2. Okay. Now, I don't know, let me see what is the time. Hey, Shakti. Hello. So maybe I will stop now or what? Okay, yeah. Let them ask some questions if they want, then I will stop it and we will continue tomorrow. Okay. Yeah. Yeah. No, surface atoms means see, when you have any crystal, because you have a finite crystal, the atoms which are on the surface means they're facing the vacuum or atmospheric. Those are called surface atoms. Surface atoms which are on the surface, simply. Number of surface atoms means you take any crystal in the cubic crystal, suppose cubic shape, it has 6 surfaces, but all the surfaces have atoms on the surface, which are is the boundary, which are on the boundary of the crystal and the atmosphere. Those are called surface atoms. They are just present on the surface atoms, surface of the crystal. And atoms which are below that, they are all the bulk atoms. They are called, because their symmetry is different from bulk atoms and surfaces. Because surface atom, it is feeling the surface bulk force from the crystal inside, which are the atoms inside, but there is no atom outside of the crystal which is bonded to the crystal. That's why you get also this dangling bonds sometimes. Bonds are dangling it. There is no bonding available in the atmosphere. Those are called surface atoms. Surface means they are just present on the surface of the crystal. So it's like that actually. Okay. No, you just give my email ID. Yeah, yeah. You can ask me to talk. Yeah, yeah.
Okay, hello.
Yeah,
Am
yeah,
I
yeah.
audible?
Yeah,
Okay,
very well. Yeah.
okay. Thank you, sir, for your talk. And just I want to know for the surface atom and the bulk atom, especially if I go for 2D structure, then how can I distinguish between the surface atom and the bulk atom?
If you go for what? Can you just say it again?
Two-dimensional structure. For any
Yeah.
two-dimensional structure, how do I distinguish between the surface atom and the bulk atom?
No. See, if you try to determine the surface structure, for example, So then what you do is probably electron diffraction or something you do. So that may give you surface structure, means it will give you at the most the few layers from the surface area. But if you